So far we've looked at the motion of things like stars in the sky or the passage of the sun across the sky on its yearly cycle. There are a couple of major things in the sky that we still need to address, one of them being the moon, the other being the planets. So first of all, let's deal with the moon. So when we're dealing with the moon, we're dealing with quite a large object, and if you look at the moon on successive nights, you may have noticed that it goes through phases. Sometimes it's full, sometimes it's half, sometimes it's a crescent. The other thing that occurs with the moon is eclipses. Sometimes the moon can go dark or a blood red colour, and sometimes you end up with solar eclipses. I'd just like to state that eclipses and phases of the moon are actually not really related. They're a different mechanism that causes each one. A lot of people think that the phases of the moon are caused by the moon and the sun blocking each other, and you end up with a shadow falling from the earth onto the moon and giving you this dark and light pattern that we see. That is not what is going on. If the moon passes in front of the sun or the earth shadow falls on the moon, you're dealing with solar and lunar eclipses. The phases of the moon are not caused by the same thing. So, in this particular class, we're going to go through the phases of the moon, and we're going to go through the mechanisms of solar and lunar eclipses. So first of all, let's just take a look at the moon. So the moon, as we see it, if you were to go out and look at the full moon, would look like this. We'll talk a little bit more about the nature of the moon while we're talking about planets. But you have these dark seas, which are called mare, which of course don't contain any water. These are basically flooded lava basins, and then you have more heavily cratered areas present on the moon. So take a look at the moon through any basic binoculars. You'll see these features in a lot of detail. The moon is really delineated into what we call the near side, which is the face that we see, and the far side of the moon, which is the other side that we generally do not see, and was first imaged by spacecraft, actually a Russian spacecraft, very near the beginning of our space age. Now, this is called the far side of the moon, and as I said, we don't see it. It used to be called the dark side of the moon, which is technically and scientifically inaccurate. It's not actually dark. Sunlight does fall on it. So sorry Pink Floyd fans, but far side of the moon is the terminology we're going to use. So here's an image of just the moon rising into the sky here, time-lapse photography, and then hitting its maximum height, and you can see it's going from the horizon higher up. The reason the moon is red when it's low on the horizon is because you're looking through a lot more dust and heavy particulates on the horizon. The moon itself is not changing color as it rises. It's simply an atmospheric effect that makes it a deeper red on the horizon than further up into the sky. And just being observant, this image actually does contain Venus up here and Jupiter over here. So one of the big questions we have is, why do we see phases of the moon? Well, the moon doesn't produce its own light. The moon only reflects light. It is not radiating invisible, it is only reflecting visible light. So all that makes it shine is sunlight hits it, reflects off, and comes to us at the surface of the Earth. So we'll come to why we see phases in a moment. But when we do see phases, this is what we'll see. You'll see an illuminated portion of the moon, this bright side, and you'll see a darker hemisphere of the moon in this case, on this side. The line between light and dark, this line running down here, that line is referred to as the terminator, and that is the delineation between light and dark due to the phase of that moon. So yes, a good way to remember it is Cyborg Killer Robots. So here's Arnie pointing out the terminator on the phase of the moon here for you. So as I mentioned previously, now we've got that terminology out of the way, we only really see the same face of the moon all of the time. Why is the question. If the moon is spinning, why do we not see all sides of it? So here's our situation. Here we have this ball representing the Earth, and we have this person who is going to move around this ball in a circle. When she is standing here, we're looking at her back. As she moves around in the circle, we're now looking at her side. To here, we're looking at her front face, and when she gets here, we're looking at her other side. So she is merely moving around while facing the same direction in this diagram throughout. If we move on to figure B, we're now dealing with a situation where this person is now spinning around. So this would be akin to the moon spinning on its axis and then rotating around the Earth. So if this person spins, by the time they get to here, we're still seeing the same face of them. When they spin to here, we're still seeing the same face again. When they come over to here, we're seeing the same face still. So if the time it takes you to go from here all the way around back to here is the same time it takes you to spin 360 degrees on your axis, then you have a situation where you only see the same face of this person. And this is what the moon is doing. So here's the same diagrams. This time we've taken out the person and we've replaced it with the Earth and the moon. So this is the first situation we had. If the moon was not rotating, it would spin around, we'd see its side, we'd see its far side, we'd see the side again, and we'd be back to the near side. Because the moon is actually spinning, and it's in what we call synchronous rotation, so one whole rotation of this planet is synchronized with the time it takes it to go completely around the Earth. Because of that synchronicity, it means we're always looking at the same face of the moon. The moon rotates, it goes around the Earth, but we always see the same side, more or less. So the time taken by the moon to actually complete one orbit is almost the same as it takes to turn once on its axis. So the moon presents approximately the same face to the Earth at any time. And this is what it looks like. If you were to a time lapse and put them together, and let's ignore phase here, but we're going from about April 3rd, if you read the date at the top, to about April 30th, this is what would happen to the moon. So sometimes you can see a little bit more to the north, sometimes you can see a little bit more to the south, but on the whole you don't see much of the far side of the moon. So it wasn't until spacecraft actually orbited the moon and photographed it that we knew what the other side of the moon looked like. So the lunar orbit, in terms of the moon orbiting the Earth, the moon orbits the Earth in 27.3 days, and it goes around in a counterclockwise direction. Now, the moon returns to the same position in the sky relative to the sun every 29.5 days for us. So that is not the same as the 27.3 day orbital cycle. The reason being that the moon moves around the Earth in 27.3 days, but the Earth has also moved a little bit relative to the sun. So it takes 29.5 days for the moon to get back to the position that we originally observed it in. A little bit complicated, but it should make sense. If the Earth is moving at the same time as the moon is moving, we have to move a little bit more to get the moon back to its original position. So this is something I've actually added in because a lot of people ask me this question in the classes, that they go outside and sometimes the moon appears to be quite big in the sky and sometimes it appears to be quite small. Well, the average angular size of the moon is about half a degree. So 360 degrees, we're in a complete circle, and about half a degree is the size of the moon. It's about the size of, say, your thumbnail. The actual apparent size of the moon does change because the moon is sometimes closer to the Earth or further away from the Earth. This actually influences our tides because there's actually a tidal bulge between the moon and the earth, and that means that we have higher or lower seawater at certain times because that bulge is moving. Let's not get into that right now, but because the apparent size of the moon changes because sometimes it's a bit closer. This effect of the changing distance gives you a change in size of about 10%. But there is also another effect. The moon can seem to change size over the course of a single night, and this is a slightly different thing. So the moon seems larger when it's on the horizon than it is when it's higher in the sky. And this turns out to be kind of an optical illusion. In fact, the moon should be smaller when it's on the horizon by about 2%. So here we have an image of the moon on the horizon with a cityscape, and as you can see, the moon looks very, very large. And as I said, we also have a bit of reddening here that's due to the amount of dust and heavy particles in the atmosphere that we're looking through. So let's ignore the colour, but the moon does appear very big on the horizon. And this is actually an optical illusion that's due to the fact that there's a lot of other objects you can compare the size of the moon to when it's on the horizon, so it looks larger. And there's actually a way around this, and if you actually want to see the moon on the horizon and you want to see the actual real size that it should appear in the sky, you can actually do something that's a little bit strange. And if you do this in the street at night and you get arrested, please do not come crying to me. And I've used Goofy here to illustrate this because these were the only GIFs I could find of somebody both standing and bending over. And yes, I realise he's looking away from the moon, but this is just an indicative sort of diagram. So here we've got Goofy standing up, and here we've got the moon actually in the sky looking quite large. Now, if you actually want to get around this optical illusion, you can bend over and look between your legs at the moon. When you do that, your legs should be in your field of view and in the foreground, and that will actually make the moon appear at the real size that it should to you, and will actually appear to suddenly be smaller. So give this a try, but like I said, don't do it in too public a place, and don't get yourself into any trouble. So let's get back to something a little bit more scientific. So, why do we even see phases of the moon? Phases of the moon are not to do with any light being blocked. So say sunlight is being beamed to us and it's bouncing off of the moon, and we're looking at combinations of bright and dark phases of the moon based on our relative position with respect to the moon and the illumination angle. We're not actually seeing any light blocked. So in this particular case, as you can see, this says to sun, and we have a new moon. The illumination source and the moon are in the same direction, but this is not an eclipse. And you can see there are times attached here. So for the new moon, the moon is going to rise at 6 a.m., be highest at noon, and set at 6 p.m. And then what's going to happen is the moon is going to get bigger in the sky. So it's going to do what we call waxing. So if it's waxing, it's getting larger, and if it's waning, it's getting smaller. So you could kind of look at it in a sort of Karate Kid way, where it's sort of waxing on, waning off. Okay? So as it gets larger, so we can see the rising time is actually getting bigger and getting later, and we're starting to see more and more of the moon. So we've now got what we call a waxing crescent. We hit first quarter. Now be careful with the first quarter because it's actually when you can see half the moon. These names refer to the orbit, not how much of the moon you can see. We then have a waxing gibbous, I'll explain this term later, a full moon, waning gibbous now, so waning moon is getting smaller, third quarter, so now we're illuminating the opposite part side, and then a waning crescent, and back to a new moon. And this is all to do with the illumination angle between the sun, the earth and the moon. And you can simulate this if you take a flashlight or a very bright light and take a ball and point towards the sun, being your flashlight, and then rotate around yourself with the ball. You should be able to see a whole set of phases. And here's the kind of phases you'll see. So we're seeing the moon get steadily larger, steadily more illuminated, until we get to the full moon, and then the moon will slowly get smaller and start to wane until we're back to a new moon. So waxing, getting bigger, waning, getting smaller. And that really ties into the 27.3 day lunar cycle that we have seen before. So here we have a situation of a new moon, appears dark, we move to a waxing crescent, we move to our first quarter. Remember, this is 1/4 of the way through the orbit, which means you can see half of the moon. Continues waxing, waxing gibbous, full moon, waning gibbous, last quarter, waning crescent, back to new moon. So the actual phase can tell you a few things about when you could see the moon. So the new moon is here, and we're looking at a waxing situation where the moon is getting bigger and bigger. So you can see up to about a half after the new moon, and then we're looking at a full moon. This is obviously an inverted scale, and then you're looking at the moon getting smaller, which is waning. A waxing moon is usually visible in the afternoon or the evening. The waning moon is usually visible in the late night or the morning. And this is the kind of thing we mean, in that we're looking at the entire cycle of the moon here and the average positions here on 14 successive nights, as it says. And this is the first 2 weeks of the lunar cycle. So we're looking at a waxing crescent. This is the 4th week in the cycle, and a waxing gibbous moon, and then a full moon. The last 2 weeks of the lunar cycle, you're now looking at this whole thing coming up later, and we're looking at the sky at sunrise here, and here's the 3rd quarter and the moon going near to the sun here. So waxing means the moon is growing, waning means the moon is shrinking. The word gibbous really just means asymmetrically swollen. It's got nothing to do with apes or monkeys or whatever. It just means, it's just a term that we use to mean there's more on one side than the other. Solar eclipses, we'll get to the mechanism that causes these soon, but a solar eclipse can only occur at a new moon phase. Okay? This is an important thing to remember. A new moon is necessary for a solar eclipse to happen. So do a little test here. The time is 9 AM. The moon is up, and half its face is bright and half is dark. What phase is it? So go back to the previous slides. You can replay these and take a look at these, or take a look through the book. It has similar diagrams to this, and you can actually tell. So I'll leave it to you to figure this particular question out, but I will give you the answer. The answer to this is the 3rd quarter. It's 9 AM, half is bright, half is dark. Check which of these 2 slides we're talking about. 9 AM, this is sunset, remember? This is sunrise. We just determined this was 3rd quarter. I would convince yourself that this is true. So our 27.3 day lunar cycle that we looked at really looks like this. Oops. Here's our new moon, here's our full moon, our 1st quarter and last quarter relate to the orbit, so we're looking at half the moon, and then we're looking at a waxing getting larger and a waning getting smaller. You do not have to memorize every single phase of the moon, but waxing and waning and knowing the difference is important, and knowing that a full moon and a new moon are opposite to one another and what that really means is crucial. The moon is not the only thing that shows phases. We will come to talking about the heliocentric and geocentric systems later, but originally people believed that the geocentric system was in effect, that the Earth was at the center of not just the solar system, but also the universe. And this became a point of great contention, and eventually Copernicus decided to come out with the idea of heliocentrism and said that the sun was at the center of the solar system, and proof was needed of this. And it turns out that any what we call inferior planets to the Earth, not meaning that they're of lesser quality, but meaning that their orbits are inside that of the Earth. So here's the Earth's orbit, here's Venus's orbit inside of it. Any planets inside the orbit of the Earth should show phases the same way that the Moon does. So observations of the maximum eastern position of Venus and the maximum western position that we call elongations relative to the Earth should show different phases. This should also be visible on Mercury, but Mercury is a very difficult thing to observe due to its proximity to the Sun. So this was done on Venus, and people looked at Venus and noticed that half was light and half was dark, and this was proof that we had lived in a heliocentric solar system, because our relative illumination angles with the planet Venus from Earth showed phases. So that's our phases of the moon. Let's move on to looking at something like an eclipse. This is actually a lunar eclipse. Often you'll see in various movies eclipses taking the moon and making it completely dark. That tends to not actually happen. A lunar eclipse is usually an effect where the moon goes a dark brown at most, but sometimes a sort of blood red color. And a lunar eclipse actually happens when the shadow of the Earth passes across the moon. So if you actually look at the motion of the moon's orbit is actually inclined by 5 degrees to the ecliptic plane. Remember, the ecliptic plane shows the inclination of the Earth's orbit relative to the Sun. So our moon's orbit is not at the same inclination as our rotational axis. So the moon is moving at 13 degrees per night relative to the stars, and its motion, that's because of its motion around the Earth, and that gives us our 27.3 or 29 day cycle for the rotation of the Earth. As I mentioned before when we talked about seasons, a lot of ancient civilizations actually used the moon as a calendar instead of the stars. If you use a lunar calendar, you'll actually end up with years that have 13 months in them and not 12. So what were we talking about in terms of the inclination of the orbit? Well, here we're observing the Earth and the Moon. So here's the Earth, here's the Moon, and here's the Moon orbiting around the Earth. As you can see, the Sun's over here, and the Moon is casting a shadow, and the Earth is casting a shadow. So from this angle, it looks as if the Moon will come around and pass through the Earth's shadow, which would mean you'd end up with an eclipse. But in reality, here's what really happens. This is why we see phases and not eclipses. So there's the Moon traveling around the Earth. As we rotate onto our side, you can see that the Moon is coming up above the Earth's shadow and dipping back below it. So it's never actually passing through the shadow of the Earth. And this is how it generally behaves. You might notice, however, that sometimes there are two positions, here and here, where the moon is actually passing through this large plane. This is the plane of the Earth's orbit, and the moon is passing through that plane in two positions. So, moving on, let's take a look at those two special positions. So we don't get an eclipse at every new moon and every full moon because of this inclination of the moon's orbit. There are, however, 2 eclipse seasons per year. In order to have an eclipse, we need to have either the Earth's shadow falling on the moon, which is a lunar eclipse, or we need to have the moon passing between the sun and the Earth, which is a solar eclipse. That can only happen when the moon, the Earth, and the sun are all in line. So in this particular case, we have the ocean or pond, as it's shown here. We have the surface of water as the plane of the Earth's orbit, and then the moon is moving around the Earth. So every time we have a splash is when the moon is actually passing through the plane of the Earth's orbit. It is only when we have these splashes that we can actually have an eclipse. So take a look at these positions. The moon is over here. Sorry, the Earth-Moon system is over here. So the moon can be here, or it can be here, but the sun is over here. So we don't have a chance of an eclipse. The Earth moves around the sun. The moon can be either here now or here, which means we have potential for a solar eclipse or potential for a lunar eclipse. Over here, the moon is either side of the Earth and the sun are in line. So we can't have an eclipse of either type here. We can, however, have it over here, because we can have the sun, the moon, and the Earth in line, or we can have the sun, the Earth, and the moon in line, which means that there are 2 eclipse seasons per year. Whether you get an eclipse or not doesn't necessarily always happen. Whether you get an eclipse or not depends on these conditions, but you do have the potential when they are all in line. And take a look at this in the book. This figure is figure 2.23 and is definitely worth looking at and making sure you can convince yourself when you will have solar and lunar eclipses and this idea of planes of orbits. So the actual cause of eclipses are the Earth and the moon basically casting shadows. So when either passes through the other shadow, you have an eclipse. So when can you get a lunar eclipse? Let's look at a lunar eclipse first. A lunar eclipse can only occur when the moon passes through the Earth's shadow. So the order will be Sun, Earth, Moon. So lunar eclipses can only occur when the sun is fully illuminating the moon. And this means that lunar eclipses only occur at full moon. If you want to see this done wrong, go watch the Mel Gibson directed movie Apocalypto about the ancient Mayans, and you'll end up seeing a situation where one day there is a crescent moon in the sky and the day after there is a full lunar eclipse, which would obviously be completely impossible because you can't switch from a crescent moon to a full moon overnight. So, another case where Hollywood gets it wrong. But back onto the subject. So lunar eclipses only occur at a full moon. There are different types of lunar eclipses as well, and this depends where the moon is in its orbit. As we said, it can incline by a maximum of 5 degrees, but can sometimes come down a little bit lower. So in this particular case, we're looking at 3 types. A total lunar eclipse, where the entire moon is covered by a shadow, and as I said goes a kind of brown or blood red colour, is when the moon is passing through the heaviest part of the shadow. That means you end up with 2 parts to the shadow. You have the umbra, which is the very dark part, this dark cone here cast by the moon, by the Earth, and then you have the lighter part. So if you look at your shadow from any light source, you have a very dark, intense shadow, and then you can have a slightly more tenuous shadow. That's what we're seeing. So a total lunar eclipse, the moon passes entirely through the umbra, or dark part of the shadow. A partial lunar eclipse, where a chunk is taken out of the moon, this is not a change in phase, this is actually caused by the Earth's shadow hitting the moon. This here is when part of the moon passes through that umbra. You can also have what's referred to as a penumbral lunar eclipse. That's when the moon passes through the thinner, more tenuous part of the shadow. And here's a little diagram that you can find, I'll put online, but is also available in terms of looking at the book, and you can click, and you do it correctly, you can click on the various moons and you can actually see the view of the moon from the Earth. And apparently is not working for me. Take a look at that and you can play with the interactive figure. So solar eclipses. Anyone who hasn't seen a solar eclipse really should. They are about one of the most spectacular astronomical events you can possibly witness. A solar eclipse is when the moon passes between the sun and the Earth, so the shadow of the moon falls upon the Earth. Now the problem with this is the moon is a lot smaller than the Earth, so its shadow is a lot smaller. So these are a lot harder to see and less frequent than the occurrence of a lunar eclipse. So a solar eclipse occurs when the moon passes between the sun and the Earth. The next total solar eclipse is August 21st, 2017 and is visible from the United States. It's 2 minutes 44 seconds totality. That means that the sun will be completely covered by the moon for 2 minutes and 44 seconds. I once travelled from Britain to Romania for 14 hours in a bus to see a totality of just under 2 minutes. These are well worth seeing. So this is located at 37 degrees latitude and 15 longitude, and this is basically in the Shawnee National Forest in Illinois. So this should be visible to a lot of people, but it's only visible over a very small distance range, a very small range of latitudes, and I'll show you why. Here's the eclipse geometry. Here is the sun, here is the moon, and here is the Earth. In this case, we are at the correct point. The moon is at one of the nodes. It's passing through the plane of the Earth's orbit. It's passing in front of the sun relative to the Earth, and it's casting a shadow onto the Earth. Here's the umbra, the dark part of the shadow of the moon, and a penumbra, the lighter part. You will only see an eclipse if you are right underneath the umbra, and as you can see, that's a very narrow cone on the Earth. So you have to be in the right place at the right time to see a total solar eclipse. If you're half in, half out this shadow, you'll only see a partial eclipse, or if you're in this part of the shadow, what's called a penumbral eclipse, a slight darkening of the sun. Just to make a point here, technically we're actually all wrong. A solar eclipse isn't really an eclipse at all. It's actually what we would call an occultation. So when a star passes behind a planetary body, if this was, say, a star passing behind Saturn, we would call that an occultation. So really we're all wrong, but everybody in the world of science and everybody in the world calls these eclipses instead of occultations, so let's stick with the normal terminology. But just letting you know. So there are different types of solar eclipses. You have total. This is where the moon completely blots out the sun, and these are the most spectacular. You have annular. The moon and the sun are in line, but the moon is a little bit smaller than the sun due to its distance and variation in distance from Earth. So you end up with a ring instead of the sun being completely blocked out. You have what's called a hybrid, which isn't technically its own type because this can be broken down, but it's a total eclipse at some locations and it's annular to others. So people standing at different parts of the planet will see different eclipse effects. And then you have a partial. These are much more common than people think, and this is where the moon partially obscures the sun, but the moon and the sun are not exactly in line. So you end up with a bite taken out of the sun. So, solar eclipses can only occur at a new moon. The illuminating source being the sun and the moon have to be in the same direction. So solar eclipses only at a new moon. Your type of solar eclipse, it can be partial, which means we've got a chunk bitten out of the sun here. It can be total, so this is where the sun is completely covered over, or it can be annular, where we have a ring. And this is how a total eclipse would evolve if you were to observe it. So take note of the bottom diagram, that here is the umbra, this is the dark part of the shadow, and here is where we would be standing. And what's going to happen is the moon is going to pass between the sun and the earth, and that's going to make the shadow move across the earth's surface. People have actually reported seeing this from places such as deserts, where they can actually see the shadow race across the surface of the earth. So the top view is going to show you what you will see if you were standing on this particular point in South America, and this diagram at the bottom is going to show you where the shadow is with respect to the earth. And what we should see is eventually we'll see a partial eclipse, total eclipse, and then the sun will get gradually brighter again. Now this process takes several hours from beginning to end, with just a 2-minute or so totality in most cases. So let's see that again. The shadow's approaching us, a chunk's taken out of the moon, the shadow's over us, that's when we see the total eclipse, and then the sun gradually comes back. And that's what a total solar eclipse looks like. I have a number of images of this that I've taken myself, but what you can do is you can blot out the sun itself using the moon, and you can see the tenuous outer atmosphere of the sun that is usually blocked because the intense sunlight is stopping you from seeing that. So these are actually very, very impressive events, and like I said, these images don't really do it justice, and people who have seen a partial eclipse often say, well, I've seen a 90% eclipse, the total can't be much better. Those people are wrong. Go and see a total eclipse and make up your own mind, but I think these are amongst the most spectacular natural events, right next to erupting volcanoes and such things that you can possibly go and see. So that's what a total solar eclipse looks like in terms of an image. This is an annular eclipse. So here we're looking at the moon only covering up the central part of the sun and leaving a ring. So getting all kind of Lord of the Ringsy in the sky there. And then you have a partial. So this is where literally a chunk of the sun is covered up by the moon. So you end up with what looks like a sun phase, where someone's actually taken a bite out of the sun, or some kind of very large commercial for Pac-Man. So there's a total solar eclipse that we can show here, and here's the beginning, and as you can see, this is taken at 12:45 universal time plus 3 here, just to correct for the time, but it basically starts at 12:45 or just afterwards, where a chunk of the sun has gone missing, and the moon moves across the sun, blotting out more and more and more of it. You then, by about 1:55, so about an hour later, we end up with what's called a diamond ring effect, and this is a flash as the sun disappears behind the moon. You then have a couple of minutes of totality usually, where you can see the outer atmosphere of the star. And then you have another diamond ring effect on the other side, where the sun re-emerges from behind the moon. And then slowly you have a reversal of the original eclipse, and the moon moves away and reveals steadily more of the sun. So as you can see, this starts at 12:45 and ends at about 15:09 here. So again, what use is a solar eclipse? Well, a solar eclipse can tell you things about the moon. There's such a thing as Bailey's beads, as they're called, and these are beads of light shining down valleys and around mountains on the edge of the moon. And people use these as very early observations. Looking at this through a telescope, you can see these blobs of light as the sun goes down behind the moon. And as you can see in this particular image, these mountains are actually quite high. And these were observational experiments that people were doing to show that the moon was not a perfect sphere with all of its features painted on, essentially, but was actually three-dimensional and had topography and had mountains and valleys on it. So these are actually this is actually sunlight shining down canyons and between mountains on the moon. You can also learn about the sun from a total eclipse. Here you can see flares and prominences coming up from the surface of the sun that you wouldn't normally see because the brightness of the sun had blocked them out. We'll talk about flares in a little bit more detail when we get to talking about the sun with respect to it being a star. There are also experiments you could do in terms of relativity. Einstein's theory of relativity said that light should be bent by a very, very large object. So space is literally warped by very massive objects, meaning that light actually bends around them. You can't see light bending around the sun because the sun is emitting too much light. But during an eclipse, you could see a star that you shouldn't technically be able to see. So during the eclipse of 1919, a star that was located behind the sun was actually observed even though it was behind the sun, because the light from that star in the Hyades cluster was actually bent around the edge of the sun and received at the Earth. So this was an observational test for general relativity. Don't get too disappointed because this is over millions of years, but eclipses will not always be visible from the Earth. The moon is slowly moving away from the Earth at a rate of about 3.8 centimeters per year. It's slow, but it's measurable. We've hit the moon with lasers and we can measure its exact distance. Humans just happen to be living on Earth at the time when the lunar disk completely covers the solar disk. So that means that the angular size of the moon in the sky is about the same as the sun. So in about 100 million years, this will no longer happen. Every eclipse will be annular. The sun will also get a little bit bigger too, which will make the effect even worse. So enjoy your solar eclipses while you can, at least your total solar eclipses, because in 100 million years, no one's going to see one ever again. I just want to add this in just to make sure that everybody's covered and I don't get into trouble. If you want to observe an eclipse, it is safe to observe a total solar eclipse. Some people in the media say it is not, but it is only safe to look at a solar eclipse at the totality. That is when the sun is completely covered by the moon. Do not observe the sun at all in terms of staring at it. You will damage your eyes and I don't want to be responsible. People have also tried looking at the sun through CDs. Again, not a good idea. The CD does not block enough light. You will damage your eyes. Sunglasses, good for blocking glare, not good for blocking direct sunlight. Don't do that. Don't try smoking glass with a candle that some people have tried. Not safe at all. The sun will damage your eyes even with 50% of it completely obscured. So please don't do those things. Only observe directly through a solar filtered telescope, which you've bought from somewhere and have actually from a certified dealer and you know will not damage your eyes, or very, very dark welder's glass. Welders, anybody who does any welding should know this. You get a very bright flash from welding gear. If you go and buy the highest quality, darkest welding glass, it is quite safe to observe the sun through that. There are different grades of welding glass. You need the darkest if you intend to do this. That is a warning. As a complete aside, there was a time during the late 1990s when Kellogg's were marketing Pop-Tarts in Britain that were so high quality you could actually observe the sun through their mylar. This is not true of American Pop-Tarts in the new millennium. Do not try to observe the sun through Pop-Tart wrappers. We did actually contact Kellogg's and ask them why they were, for a while at least, packaging their Pop-Tarts in very high quality optical mylar. They didn't know they were. So don't do that, but it's still an interesting little story. So eclipses, they basically recur on an 18-year, 11 1/3 day cycle. Don't worry, you don't have to remember that number, but that's what it is. And it's called the Saros cycle. The type of eclipse that you see can be partial, it can be total, and will vary by your location on the Earth. Well, let's take a look at some of the paths. And here's all of the total eclipse paths between 2001 and 2025. So some of these have gone, some of these are still to come. So here's the 2006 eclipse going through Libya. Here's another one where the totality in 2001 was actually in the middle of the ocean here. So the one we are getting excited for is the 2017 eclipse, which runs completely across the United States, giving us maximum totality in Illinois and then out over the Atlantic. After 2017, you may be able to go out into the Pacific and see a good eclipse. Here's another one in the Pacific in 2016. And then after that, you're really looking at going to some far-flung places such as Antarctica to see these things. And this key shows you total, annular, hybrid. I've turned these off and only showed you the total eclipses in this particular case. Going to this particular website, the GSFC website, you can find all the different eclipses all the way up until something like the year 3000, should you really want to. So the 2017 total eclipse, here's a little animation of the 1999 eclipse. August 21st, 2017 at 1826 hours and about 2 minutes 40 seconds of totality. Don't miss it. So there are two conditions for an eclipse. It's got to be a full moon for a lunar eclipse or a new moon for a solar eclipse, and the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane. Those are called nodes. So those are the splashes if we were looking at this in terms of, say, a pond. Remember that. And here's a summary. I'm not going to read through the whole summary, it's there for your information. As I said, you don't have to remember the particular amount of years it takes for the cycle to repeat. Okay, that concludes our discussion of lunar phases and eclipses.